All right, let's keep working on areas. And now let's assume that the function f of x is negative. So the region looks like this. I have my y equals f of x, and it's below the x-axis. When we construct our Riemann sums, same formula as above, then f of xk will be negative. So if this, I'm dividing into region, if this is my x3, let's say, f of x3 will not be this length, it will be minus this length. So minus the height of the rectangle. All right, so each f of k will be negative, so these will give minus the area of the corresponding rectangle. So delta x f of x3 will be minus a3 if I take this as a3. And so Sn will be a good approximation for minus the area, and hence the integral from a to b will not give you the area, it will give you minus the area of this region here between y equals f of x and the x-axis. All right, so if it's positive, you get positive the area. If it's negative, you get negative the area. Now, what about a function that switches signs? So for a general function f of x, the integral will compute the area for the interval in which f is positive and will give minus the area for the integrals on which f is negative. All right, so for something like this picture here, the part that's on the positive side, that will get computed positively. And then the regions that are under the axis, that will get added negatively, will be subtracted from it. And so if I have something like that, so the integral from a to b of f of x dx here, if this is a1, this is a2, this is a3, and this is a4, it will compute minus a1 plus a2 minus a3 plus a4. Everything that's above will be computed positively because f there will give you the height. Everything that's below will be computing negatively because the function f of x will not give you the height, it will give you minus the height. Hence, the definite integral calculates a signed area that we will call the net area. All right, so here's the definition of net area. The net area of a region R is the area of part of the region that we'll call R plus minus the area of another part of the region that will be called R minus. All right, so R plus is the part of R above the x-axis, and x minus will be the part of R below the x-axis. All right. And so like we said, for any function f of x defined on the interval if a, b, then the integral from a to b will be the net area of R, where R is the region bounded by y equals f of x, y equals 0. So between those two curves, from x equals a to x equals b. Right, so in example 4.1.8, we will evaluate the following integrals using net area. Right, so using R plus and R minus in all of this. So to do this, we'll have to sketch the region. So let's see, what do we have? So we want from minus 2 to 3. So minus 1, minus 2, 1, 2, and 3. Perfect. All right, so we want to graph y equals 2x minus 4. This is a line. All right, so let's put a few points and then we'll just draw the line between them. If I plug in 3, I get 6 minus 2, I get 2. So 3, 2. Then at 2, I will get 0. I will get, that's 3, I will get minus 4 right here. And then at minus 2, I'll get minus 8. Minus 2 minus 8 will be this one. All right, so here's my graph. And now we're ready to sketch the regions that we have. So we're going to look at this region R here. So this part plus this part. So everything that's above the axis will be counted positively. So let me sketch it in green. Everything that's below the axis will be counted negatively. So let me put it in red. So when I take the integral from 2 to 3 to x minus 4 dx, I will have the area of this part of the region minus the area of the red part, of the part that's below. All right, so we need to figure out these triangles. Well, of course, we'll be using base times height over 2, but we have to figure out what their base and their height are. All right, so for the base here, I have 1 from 2 to 3, and then my y component is 2, so the height here is 2, because this is 2. So the first one is 1 times 2 divided by 2. And then I'm going to subtract the area of the red one. I'm going from minus 2 to 2 here, so this length is 4, so the width or the base is 4, and then the height is this length here. I'm going from 0 to 8, so this length is 8. Notice it's not minus 8, and that's part of the reason we have to make it negative, is the function is not giving you the height, it's giving you minus the height. All right, and then we'll get 4 times 8 divided by 2, so I'm getting 1 minus 16, I'm getting minus 15. All right, so it's not computing an area because minus 15 is not an area, it's a negative value. But this is the difference between the part that's above and the part that's below. So it's telling you I have 15 more units of area under the x-axis than I have above it. All right, let's try another example. I have this integral here from minus 5 to 8 of absolute value of x. So y equals absolute value of x. That looks like a v, something like this. So I want to look at it from minus 5 to 8. So this is 8, 8, and this is minus 5, 5, and so here's our region. Notice that the entire region is above, so everything will be in green. And so I just have to compute the area in this case. There's no negative region. So I'm going to take the area of both and add it. Here I have 5 units, and I have 5 units here. Here I have 8, and I have 8. And so I'm getting 5 times 5 divided by 2 plus 8 times 8 divided by 2. And I've computed this, it's 89 halves. All right, so at this point, we understand what we're calculating. We know it's the net area, we know it's the area if it's positive and all of this. So we can see how for simple region we could use the areas to compute the integral, but that's kind of backwards. We want the integral to be able to compute area. So now we're going to start using algebra and our formulas for sum in the next section to compute the integrals of functions that are not straight, right? So far it's straight and then circles. That's all we've been doing. We're going to do more complicated regions. We're going to do parabolas and all of this, and we'll be able to do it using the formulas that we saw in section 4.1.2.